Good morning. This is a talk about an intelligent namespace. Current software development, our namespace is predefined by the compiler as being an external search for names and values through programming. In Jane, my software development system, we're looking for a more intelligent namespace, one where everything's in context. This is me, Cliff Collins, computer science major. I went to a single data structure, which is a cell, and then all information is stored within the cell. But the cell is complex. It is a load-on-demand system in which we can reference something, let's say a file or a database or something, but nothing gets done until it actually is used. So if I said, drive a temp file, I can say that, but until I actually reference that or use it in a statement, it does not get loaded. It means it's not read, and we only need one record at a time. So it does static and dynamic allocation of memory, all the values. So languages like Fortran and C++ and COBOL all do static memory allocation of named variables. So this is at compile time. JavaScript and C# and some of the newer languages do dynamic allocation, which means that you can create them during runtime. The cell is both. It's dynamic and static, so that you can declare C++ type of declaration statements like JavaScript. You can just name something and have it allocated at compile time and runtime. Physically, it has a cell can have values, properties, if you will, but it can also have folders. And folders are separated in basically two types of information structures. One is functionally related cells, which mean this is information that relates to the content of the cell, only functional, something like a sort index. Yes, a cell is sorted, but we store this sort index separately, and column names and all the related information. We also have logically related information, and these are things that are related to the cell or the content of the cell, such as source code. Okay, here's the logic relating to it. The source code, though, is actually not related. It's just simply if I needed to recompile it or look at it or have documentation associated or contracts or whatever related to this particular, I can store that there. And then we have the properties of the cell, and then we have a root folder. So every cell, if I have a number 23, it has this same structure. Of course, this is all load on demand, so if we never reference any of these or reuse them, they don't get allocated. So it's just simply a convenience for software development to be able to have all this logic attached when it's required. And each cell is associated to a term, so it's a cast term. Let's say an integer, or a counting number, or a whole number, or a person, or a car. It's related to some term, and we can cast that. So let's say we had an integer, we could cast that as text, or we might cast it as a binary representation or a hex representation. By casting these, and these are all centrally located within the cell, so the cell itself knows what it can be cast as. And then we can have qualifiers. So if we have a cast and let's say an integer, and we can qualify that. So we can put a range in it, or representation, or language, German or French or whatever, qualify a particular value. This cell has a location. So it might be in memory, it might be on disk, it might be on a remote machine, and then we also have security. Okay, so we have this cell, and we have our whole structure of our system is related to this, and we want to be able to name search it. So our searches, we've broken it up into a syntax, so the properties of the cell. Let's say A is our cell. So A dot is the names of the cell's properties. And we have that folder, our root folder, so it's A/, and that's the names of within our root folder. And then children, which is our functionally related properties associated to the vertical bar. And the parent is the backslash. So the parent of some container that's the parent of A is represented with a backslash. We have recursive name searches, so we can have a nested cell structure, and we can search the whole structure by using 3 dots. We can associate name wildcard property name search simply putting quotes around it. So A dot is the property names of A, so we can search that with wildcards by putting it in a quoted string. And then we can do a SQL name search by putting a question mark. And then we can do value search. So wildcard property search, value search is, in the first example, we used A dot. Here we take the dot out, and now we're searching the content of A. So the values of A. And we can do the same thing with the SQL search. So these are some of the primary concepts that we're looking for. Is we need to be able to access everything, all the values that we have as our database. And to extend this a little bit, we extend the SQL and do all the statements of SQL and just not the select. Qualify our cell structures or what we want to search. So the @ A is the cell structures. The cell has a structure, and that structure is the database. So we'll want to look at all the subcells of A. So we get to see what the content of those are. Generally, these are hidden in the compiler. The compiler doesn't let you see these things. I'm saying, why not? So we're going to do that. Further extend this, we can use the # for saying I only want the numerically named properties, or the ampersand to say I want the alphabetically named property. So we can treat a cell as anything we want. Okay, so we'll look at the dot named and numbered properties of a cell. If I only want the names of the properties, I can just say X dot, and that will return the names. Or I can specifically give a name and say, I want the value of X dot A. So I want one of the named property, or a numbered property. So I can say X dot 1, and that will give me the first one. And combined use. So here's an example of A, B, C, and D. A, I'll just assign A to be example.A, and then A / dot is actually, the backslash is the parent, the dot are the names, so we can reference anything through our name search logic syntax. And the backslash is the parent cell. You can use an unnamed backslash as the parent of the cell. A named backslash is one of the siblings of, and I want one of my siblings. / is cells related children. A / is the names of the root folder of A. And then we can reference one of the values of A. So here we have computer this, so we're the whole universe of digital information as one namespace. To the user, everything is simply part of the namespace. So computer this .disk drives /C is one of our disk drives, our C drive, and in a folder called temp. Within that disk drive, I took the dot out for our extension and just said example text. We have C dot available 1024 byte blocks. Each cell, C is a disk drive, and that cell that represents C, the casting value, parses its own namespace. The available 1024 byte blocks, we could actually take that, send that to C. C is going to have reference to this, and then we can change that number and say we want 512 byte blocks. Very, very dynamic in our capabilities of what we want to represent within our namespace. And we look at the third example here. So we look at one of the display.dll files, and that becomes part of our namespace also. So Jane is able to read all the binary structures and treat it as an object. So it's a structure, and we can get into that structure through our namespace. So we can get to the sections, and the sections have a name and a size and all the values that we represent by our binary structures. Vertical bar is functionally related folder, which is those things that we use within the context of A which is maybe our sort index. Names or property names in all these cells are stored in a binary tree, and then that binary tree creates a sort index. And here we can have access to it. But there again, we have to remember that this is all load on demand. If we never use this, there's no cost. And then name related operations. So we have further syntax which says I can use this bracket to reference more than one variable. A might have 100 names, but I only want 2 columns out of it. Or I can put a number in there. Operator base. So if it's a number, it's treated one way, and that's why this cast value allows any kind of syntax representation within each data type. So if we did a substring, we could do Cliff as a text, and then I can just say I'm going to represent the character positions and extract those. Function arguments, generally we have the name of the function and then input argument, but I also want output argument. Do call test with A and B, and I'm going to be returned C and D, multiple arguments. We can do the assign. By doing this, we can stick this test function inside of a conditional, and then the SQL statement. And then we can have system defined properties. The brace to say these are predefined system parameters. I want to see the structure or the date created or any of these system parameters that we define within Jane to be universal and then predefined and programmed for you. And wildcard searches, so we can do single characters or multiple characters or kind of things. We could do, we could put in regular expressions if we wanted to. For now, we'll just use simple wildcards. And then if I did regular expressions, I would extend it. There's only about 6 capabilities, and most of the regular expressions I quickly defined about 29 other capabilities, like go search for an address or search for a phone number or search for a URL or and then we do a wildcard value search, which is simply take the dot off. And we can do user defined name and value search syntax. Declare that for data type Apple or something, then we can ask for its geographic location, and then that geographic location can be complex. Writing applications across multiple machines. So for you, it looks like we only have one application, and then that application is actually run on multiple machines. And so the name resolution is done at the point of contact. Here, if we have like that disk drive example, we'd have to send that down to the machine and have it resolve it, because we would not want to pull in all the values of that machine into our machine. We just want to go get maybe just the size of some file. We don't need to pull a file in. And so that name resolution is done where it is most efficient. And we have machine dependent resolution. So each machine, if it's a wash machine or a refrigerator, it has its own context and would do its own name resolution and then return the value. And that's why it's somewhat why the SQL statement is in there, so that we can alter, create things through our name resolution on remote machines. And it's optimized logic. So if it's a extremely huge file, we could do memory mapping, optimize our name resolution, searching for things, doing it on demand. So if I have 1 billion records, I can only see 22 of them maybe at a time, so I just load the ones I need, and that's all tied in through logic, so we don't do any programming. So that all logic is automated. Jane does all this for us. We just simply need to tell it what we want. And so to the user, it just looks like one machine, one address space. That's what we're after. Okay, that's kind of a brief overview, very trivially brief overview. There's much, much more to it, but I wanted to describe some of the context and what Jane is going to accomplish. Thank you. Until next time.